Aloha and greetings. Welcome to episode number 2 of the Planets Foundation's Life on Planets weekly YouTube live event. Today our topic is large telescopes for exoplanet research. My name is Kevin Lewis and I'll be the moderator for the live event today. We're joined by a distinguished group of scientists and professors who are also both members of the Planets Foundation Consortium. We have a simple format for these events. If this is the first time that you're viewing it, I'll just give you a little intro. They're roughly about 30 minutes in length. And each week we connect you directly with the professional astronomers that are creating the technologies and techniques for finding life in the universe. If you're viewing this event live and you want to engage with us directly, you can tweet us your questions using the hashtag #LifeOnPlanets. Or you can also send us an email at hello@planets.life. Lastly, if you like what you see and you want to pledge your support to make sure that these hangouts continue, please visit our Patreon page at patreon.com/planets, where your donation will also go to the creation of our telescopes to find life in the universe. So today we're joined by 2 panelists. Our first guest is Dr. Jeff Kuhn. Jeff is a physicist and an astronomer, having received his PhD from Princeton. He has a really innovative optical research, and he's contributed to telescopes now under construction like the Giant Magellan Telescope and the DKIS telescope, for which he is a principal co-investigator. And he also leads the Planets Consortium. And then we're also joined by Dr. Marcelo Emilio. He just joined us all the way from Brazil. He just arrived yesterday, isn't that right?
That's true.
Yeah, perfect. So thanks for joining us. And he's an astronomer from the Ponta Grossa State University in Brazil. Hopefully I pronounced that somewhat
That's correctly.
Good. He is one of the discoverers of the first ring around an asteroid, Chariklo, and with collaborators was one of the first to use measurements of planetary transits from space to measure the size around the sun. So thank you both for joining us today. Appreciate your time, and let's just get right into our questions. So the first question we have is from Connor, and he asks, I'll address this to you, Jeff. So we have a lot of telescopes in the world. Basically asks, why do we need them, and why are they so expensive to build?
Well, there's lots of sky to see, and lots of sky to see over a lot of time. So the time variability and the resolution to see objects requires lots of capability. The major telescopes that you've heard about, like the Keck telescope or the large telescopes over on Mauna Kea just next door, all are heavily oversubscribed. Astronomers from all over the world request time to be able to do research with those telescopes. And you have to almost win the lottery in some cases to be able to get a few hours of time. There's so many fundamental questions that we're struggling with, and they all require some, we call it remote sensing, some ability to learn about these distant objects by collecting the light and then splitting it up in a lot of different ways. So it's not just the different telescopes that multiplex to the sky, but it's also all the different instruments that can't all be used simultaneously. So it turns out that it's actually a subject, observational astronomy, that doesn't have as many telescopes as it needs to address the problems that we're able to try to answer right now.
Okay. You know, that's something I've actually always wondered. So how does you said you almost have to win the lottery. How does that work? Especially like every time I hear astronomers talking about Hubble, they're always talking about how precious the time is. How does that lottery usually work in telescopes? How are you awarded time? Is it literally just luck of the draw or science case?
Yeah, you want to answer that, Marcelo?
Well, each telescope have his policy, but normally you have to present like a scientific project to get time. How bigger or more expensive the telescope is, more complex with more detail your project needed to to have. And they also have some opportunities and time of the director. Sorry that sound, because I cannot hear anymore.
Oh, you can't hear?
No.
Jeff, can you unmute yourself?
Yep, I'm unmuted. I can hear you fine, Marcello.
Okay. Yeah, we could hear you just fine.
Okay. Okay.
There was a little bit of feedback, so I muted Jeff to get rid of that feedback. So I don't know if that changed anything.
Okay. Basically, to have time in a telescope, you have to explain in detail what you want to do and how much time you need. Then there's a group that will decide if you have time or not. Normally, they have more requests for time than available time in telescopes.
Right. Okay. Gotcha. Great. So the next question is for you, Marcelo. So Planet's foundation, actually all of the telescopes are off-axis. Can you explain what off-axis means and why they're specifically designed that way?
Well, off-axis is a way to avoid obstructing the coming light, moving the secondary element of the primary axis. This will avoid the light scattering and allow us to see very low light objects near bright ones.
Okay, so essentially, just because there's no, I don't know the right word to phrase it, but cross beam, since all the light's going right into the primary and then right into the secondary, it's all unobstructed light. There's nothing scattering.
That's true. Not avoid the light scattering.
Okay, and how come like all telescopes aren't designed that way? It just seems like it makes sense that all new telescopes would be designed with an off-axis. Are there benefits of it being built the more traditional way?
Well, that allows to see objects very close to point sources. That you have a bright source and allows to see objects near that source.
Okay.
I think what Kevin was asking was, I think that it's relatively new to build off-axis telescopes optically. Why aren't all telescopes? Why haven't they always been off-axis telescopes?
Good question.
And I can take a stab at that. Part of the reason is that off-axis telescopes are slightly harder to align, and their field of view can be less. It means they, at a single pointing of the telescope, for the same curvature in the optics, you get to see less of the sky. But now with modern polishing techniques, it's possible to make mirrors and optical systems that deliver superior optical performance. We say diffraction limited. It means that you can see very fine detail in the sky with off-axis optics, which in older times would have been more difficult to do. The simplest optic you can make is something that is concentric and symmetric, so you can use that symmetry to do alignment. In an off-axis optic, it's often advantageous to use computer systems and complicated, slightly more complicated, for modern technology, not really complicated at all, but to use more technology to do the alignment.
Okay, that makes sense. So Jeff, next question for you actually is specifically on the mirror polishing techniques. Can you explain a little bit more about that and how they work and the different types of new mirror polishing techniques available?
So the reason why telescopes are so expensive is that they have to be very precise in their ability to point in the sky. And they also have to have a very precise shape. They have to create a shape which is accurate to a fraction of the wavelength of light, which means it means that it's a tiny, it's a very small number. It's millions, much less than millions of a meter. They have to maintain that shape. And so polishing is the reason why telescopes are expensive. Typically, the cost of the glass is maybe 10% or less of the total cost of a mirror. It takes time to do the accurate grinding of the glass, and then the measurement, the metrology, to see that you have a shape that you actually require to put light in the right place to make an image, is what makes it so expensive. So a conventional mirror, which is polished by rubbing and removing glass, could cost something in the neighborhood of $500,000 per square meter, if you add up all of those costs to shape it. To go further with large aperture telescopes and make them affordable, relatively affordable, we need new technologies, and one of them is something called deterministic polishing, using machines that are relatively inexpensive to build. Our collaborators in Mexico, at the university in Mexico City and in Ensenada, have over the last decade created a technology that uses basically water propelled at velocities faster than the speed of sound, even in a very specially designed nozzle, to create a way of removing glass in a controlled way without applying pressure to the glass. It's called Hydra, and Hydra will be used to polish our first Planets Telescope Foundation mirror, which is a 2-meter mirror. That makes the polishing less of an artwork, less of art and more of science, and that technology is called deterministic, because once you measure the shape that the mirror has and you know the shape that it needs to have, it takes only a couple of passes of this fancy machine that uses water to create the shape that we need. Ultimately, the way to polish glass is not to rub on it at all, but to use glass which is very smooth. Once you rub on glass with either a water system or a grit and a grinding motion, you produce a surface which is relatively rough and scatters some light. And we don't see that very much, but in a telescope that's designed not to scatter light, we care about the diffuse scattered light of the surface. So the other technology in all of this then is to never rub on the glass, but to take glass that's thin enough that you could shape it. It's called active optics to some scientists, and now with 3D printing technologies and special algorithms that use a bright star to determine the shape of the mirror, it's possible to never have to polish the glass, to construct it with essentially window glass sandwiched with some printed structure in between a couple of sheets of window glass that can then have the perfect shape for forming an image. Now, of course, has disadvantages. It requires a bright star in the field of view in order to create that nearly constant updating of the shape to keep a good surface. But it ultimately is much less expensive, much faster, and more importantly, even more lightweight than conventional mirrors that have to be thick, because they have to maintain their shape against things like changes in the pointing angle of the telescope or the temperature of the air that would affect the shape. With an electronic mirror, it's possible to make all of those adjustments dynamically. And that's the real future of telescope mirrors, is to use information technologies to make them have the right shape.
Right, that's exactly what I was just going to comment on. It seems like in the last few years that the active optics has really improved to even be able to do this, where you're not really having to worry about polishing it so much. You can rely on the adaptive optics of the mirror to do the work for you. Is that kind of right?
Yeah, it is. Well, astronomers are a little bit more specific about the kind of shape control of a mirror. Adaptive optics is a term that refers to very fast adjustments in a very small mirror. And those adjustments are made to adjust for and compensate for atmospheric turbulence, the seeing effect that the atmosphere produces that makes stars twinkle. So adaptive optics is sort of the same idea, but it's done in a small mirror, typically maybe this size. Active optics is the adjustments that need to be done on a slow time scale, say as the temperature of the telescope changes or as it slowly tracks a star. And the active optics is something which hasn't been done on a large scale, and it certainly hasn't been done with window glass. And that happens on very large scales. The kind of mirrors that we're working on now are mirrors that could be 8 meters across, made of window glass, that have many thousands of wires printed on their backside that have force sensors and force actuators, and then an optical system that's able to understand what the actual shape of the mirror is. So we call that active optics. The stuff that you hear about for correcting the turbulence in the atmosphere is adaptive optics. And any new telescope, any modern telescope, will have both components to manage slow and fast effects in the deformation of the light that comes from a distant star.
Okay. Yeah, that's interesting. I can't wait till we have these in place and they are looking at the sky.
Stay tuned.
Yes. So Marcella, next question for you. We actually already answered part of the second half of the question, but Connor from online asked, who is the owner of each one of the Planets Foundation telescopes? And then he also asked, who controls what you observe each night? But can you talk a little bit about I guess the owners per se, or who owns these telescopes?
Well, Planets, it's a consortium, and there are many university and institutions involved in Mexico, in US, Brazil, in Japan, in Finland, and Germany. Jeff can correct me if I forget someone.
The overall organization that we're part of includes many countries. It's growing. Brazil, that Marcello represents, is recently come on board, and it also has some private foundation money. Searchlight Observatory is an organization that's operated by Casey Harlington, who lives up in Vancouver, and he's been an early contributor to the technologies and to the program that we're working on. So it's a broad collaboration.
Great. I mean, most large telescopes are pretty big collaborations. It's not normally just one owner, right?
That's true. Some universities over the years have managed to acquire their own interests, and so that gives them special advantages in how they allocate the time. The Planets Foundation is dedicated to this concept of understanding atmospheres of planets and the search for life. And so our program is focused on the users that will help advance that, or the technologies that we need to demonstrate that take us from the current technologies in our big telescopes to the future.
Right. Gotcha. Makes sense. Next question is for Jeff. We've already answered this a little bit, but maybe you can give some more details. What makes telescopes that the Planets Foundation wants to build so different and special? You already talked about the deterministic polishing, talked about off-axis. Is there anything else other than those two that?
Sure. Well, Marcello mentioned the off-axis fact. We care about we're always looking at objects, faint objects that are close to bright objects. That's what exoplanets are, or the atmospheres of, even in the solar system, finding the exoatmosphere, for example, of Mercury. Mercury is very bright compared to any light that we might get from this transient atmosphere. And so that requires a telescope which is specially designed to have this off-axis feature, to have a smooth mirror, and ultimately to have other tools, instruments that make separating the good light from the bad light. By that I mean the light from the faint exterior of the star or the planet from the bright scattered light of the star or the planet. And the tools that we use for doing that also involve instruments at the focus of the telescope, and those instruments use specialized tricks. Coronography is one of them. Polarimetry is another one, and well-performing adaptive optics will be another part of the tricks that the Planet's Telescope Foundation instruments will depend upon.
Right, yeah, I would imagine that the instruments are a large component of what you're able to do with the light once you collect it. Obviously, you need to have really good instruments to analyze and process and look at that.
Indeed.
All right, so next question for you, Marcello. So other than Colossus, this actually comes from a Cloudy Nights member, Thornhill is his name. So other than Colossus, there are 3 other large telescopes that I know of called the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope. He wants to know, what are the main science cases for these 3, and then also how do they compare to the Colossus telescope as far as how they get information about exoplanets?
I was checking the science of each telescope. They're all trying to explore the frontiers of science. They want to know what dark matter is, for example, and probe extrasolar atmosphere, try to find if those extrasolar planets have life. And also, they try to study the formation of the first stars and the first galaxy in your universe. The off-axis telescope have some advantage because we will have less scattered light that allow us to go further, exploring exoplanet's atmosphere, for example.
Okay, but is GMT off-axis or no? Am I wrong about that?
No, they are not off-axis.
Okay, none of them are.
GMT, ELT, TMT are off-axis.
Gotcha.
So
Yeah.
let me amplify on what Marcello said, and that is the current the 3 upcoming, call them world's largest telescopes, are each designed to create a single primary mirror with a fixed shape. So they all use edge sensors, so each of the mirror segments are locked in phase by an electronic system that maintains their shape. And for various reasons, the mirror segments themselves are small, and they have a small gap between them, something of order of millimeter.
Right.
So that's bad for problems that seek to minimize scattered light. That those edges are like a crack in a fixed sheet of glass, and that the crack scatters light. That light scattering ultimately is the limitation in optical systems that use many mirror segments. So there's some design strategy, and the reason for that is those telescopes are driven to that solution because they have to produce basically a single surface to generate what we call a wide field telescope. These are telescopes that are going to look back into distant parts of the sky, but they need a relatively large angle. They're not looking at a single star like the PTF telescopes are. They're looking at a region in space, and that region in space requires a different kind of optical system, and that makes the PTF telescopes very different than these other general purpose astronomical telescopes. So the Giant Magellan Telescope and the 30-meter telescope and the European Extremely Large Telescope have to serve the worldwide community of astronomers, which, as Marcello mentioned, are interested in things like the earliest phases of galaxy formation, or where quasars come from, or how do galaxies cluster as you look back in space and time. Those are problems that require a field of view, and they can't be solved by a telescope that looks at just a single star, as Colossus or ELF would do. So the main difference between our telescopes and theirs have to do with this field of view and scattered light issue. We don't want to have lots of near segments with a gap between them that scatters light. We try to minimize that in a big way, and that's important for this different class of problems related to learning everything we can about exoplanets.
Right. All right, thank you for that. So next question is for you, Jeff, and this comes from Thornhill again from the Cloudy Nights forum. Seems like it's a little bit of a complicated answer, but I will try to formulate it as best as I can. So he's wondering about detection thresholds for something like the Colossus. So essentially what he's asking is, let's say there's two similar planets, let's just call them like they're identical to Earth. And let's say one's 5 light years away from Earth. And let's say another one's 75 light years away from Earth. What he's wondering is the one that's 5 light years away, are we going to be able to see more of an advanced civilization on that one that's closer versus the one that's 75? So in the sense, like, if we're looking at one that's 5 light years away, we'd be able to see a civilization, if it had it, of course, as advanced as ours, and the one that's 75 light years away, we'd only be able to see like simple organic life. Can you explain kind of how that works? Like the farther away the system is, what you'll be able to detect?
Well, that's a really complicated question, and people write entire scientific papers on just pieces of the answer to that question. But let me bite off a couple of small chunks. So the first point is that we don't actually know what the right, call it a biomarker, is for civilization. The Planets group, some of our collaborators a couple of years ago wrote a paper that said, well, the best biomarker for civilization, advanced civilizations, is the heat that they generate. Life is really about energy. And so life ultimately produces heat, and it could be distinguished possibly from the heat that comes off of the planet just because it's heated by a star. That's particularly true when you think about a planet that rotates. So as a planet rotates, imagine that Los Angeles comes into view on our side of the planet. We're a long way away, and we see a planet that's, call it an Earth copy, in Los Angeles, and the Pacific Basin civilization there rotates into view. That heat we could see. Well, we have to be able to distinguish it with enough sensitivity from the background glow of the planet. And so we've done some calculations to show that if you have a telescope, which is about the size of Colossus, that within roughly the nearest 60 light years of the sun, which is about 20 parsecs in astronomical terms, we could possibly detect advanced life by its heat signature in roughly 100 or a few hundred. Now, the civilization that we could see depends on the separation of the planet from the star, because the glare of the star will obscure the light, that thermal signature, if it gets too close. But that also depends on how far away the star is. So the answer to this question of how do you find advanced life depends a lot on how close. So, for example, the recent potentially terrestrial, potentially water-bearing planet around Proxima Centauri is a tiny fraction of an arcsecond away from its star. We'll have a hard time seeing life or advanced life or even any of the light from that star until we get bigger telescopes. And the way that works is as the telescope primary mirror gets bigger, the light is more concentrated, and so the starlight is more concentrated, and the glare doesn't spread out into the image space where the exoplanet lives. We won't learn much about Proxima Centauri until we get a telescope like ELF built. When it does, we could very well detect both biosignatures and civilization signatures. There are other potential markers. So the primitive life signatures are often spectroscopic. They're just, for example, evidence of oxygen or gases in the atmosphere that don't last very long. they get combined chemically or they're reactive. Unless there's, for example, if there's plant life, we might imagine that photosynthesis would produce that oxygen signature in a spectra. And you're right. Some of those biosignatures we can see more easily than, for example, the advanced civilization signature. But it's not obvious, and it depends on details about how civilization evolves and how it produces heat, or how plants actually evolve in other environments. The plant signature we might find by just looking at the red edge of chlorophyll, where we could add up a lot of photons in order to see a transition from the red side to the blue side of that chlorophyll transition. Those are areas of active research, and unfortunately, the basic answer to your question is we won't really know about life until we get telescopes that are big enough to separate the light of the star from the light of the planet. And once we do that, we'll be on our course, really, for both civilization signatures and for biological signatures.
Right. So first step is obviously have a telescope that can even do it, and then figure it out from there. So one of the questions I get asked when I'm talking to people about it is like false positives. So maybe Marcel, maybe you can answer this. Whether you're looking for heat signatures or you're looking for oxygen or methane, how do you weed out a false positive from a heat signature being active volcanoes, or are there other non-biological processes on planets theoretically that can create oxygen? I mean, how do you know with 90% certainty that isn't just something that's happening on the planet that's not organic?
Kevin, I don't have experience to answer that question. Maybe Jeff can help me.
Yeah, so the issue of when you're looking for a thermal signature, one of the things that we have to do is so a thermal signature happens with temperatures that are slightly in excess of the background. So the heat that we use power, we use energy, and we create heat, and that heat is just a little bit warmer than the background temperature. That's the most efficient way of using power, if we can dump the heat at a temperature which is just slightly above what we call the thermal reservoir that we live in. So the heat signature of photosynthesis of plants, or the heat signature of a civilization, will most likely be at a low temperature, close to the temperature of the planet. The heat signature of geothermal activity or other things is at a much higher temperature. And so in these optical schemes, we use different wavelengths of light to be able to disentangle the different causes of the signal. But the answer to your question is we will never be 100% sure. And there's always some uncertainty, and that uncertainty goes down as we collect more observations. And then, of course, there are some planets for which we're just hopeless. Imagine looking at Venus and trying to understand from 10 light years away whether or not Venus actually has anything underneath its cloud layer. I don't know how to go about addressing that. We'll learn about the clouds and maybe the chemistry of the clouds. But learning about, for example, the possibility of some curious creatures that can survive at the high pressures and high temperatures of Venus, we can't even do that now from Earth looking down from Venus. So the answer in some cases is we won't crack this nut. It won't be resolved with big telescopes. But for many cases, Earth-like cases, I think we have a lot to learn.
Right. And it seems like looking for the specific heat signature is the best bet. I mean, I guess looking for atmosphere gases like oxygen and methane are great too, but it seems like the heat signature seems like it's one of the best bets. Is that right? Or
it has the advantage that you can add lots of photons in a big band. If you're looking for oxygen, you have to look for these narrow wavelength bands, and so you don't have a lot of photons unless you build a system that averages lots and lots of different wavelengths. That's not completely true. We're looking for, as I said, for chlorophyll, or photosynthetic molecules is in some ways easier. But the thermodynamic signal certainly has its advantages. It has the disadvantage of that we have to look through our own atmosphere, and unfortunately we can't completely avoid that. But there are tricks that we can use to distinguish what our atmosphere does from what an exoplanet, a distant exoplanet, does.
Right. Gotcha. All right, and then the last question is for you, Marcelo. It's also comes from online. So I know astronomy is international. What projects are you working on in your country, Brazil? What projects is your university working on, and any new projects that Brazil as a country is working on as well?
I particularly are working in measuring the size and shape of the sun. I also participate in a group that tried to measure the size and the shape of trans-Neptunian objects as Pluto, Aries, some object that we call TNOs, trans-Neptunian objects. Also, there are groups in Brazil that try to find the solar twin, a star that we cannot distinguish from our sun. Many people studying chemical evidence on star, and there's a scientist in São Paulo that studied one of the most massive star in our galaxy, the Eta Carina.
Okay. And other than the obvious, what let's say we found the sun's twin. What would that mean, and what would we be able to? What's the significance of that?
Well, what people try to do is to find the solar twin in a different age of our sun to study how the sun will evolve, and how different we are. What make our solar system have life? Is the sun really different from other suns out there? What make possible our solar system have life?
Right. And have we found any sun that's pretty similar, or you said you're working on it, your team's working on it?
There are some candidates, a lot of candidates, but up to now, as far as I know, that's not identical sun. There's some problem with the evidence of leaking. Looks like
evidence of leaking.
Evidence of a chemical element called lithium.
Okay.
It looks like different from our stars, or there's some people who claim that there's some difference in the lithium.
Gotcha. All right. Well, thank you for that. And we're about done with time. It's 39 minutes, 40 minutes later. So thank you, Jeff and Marcelo, for an interesting discussion this week. Appreciate your time, and hopefully you'll be able to join us for future Hangouts in the future. And anyone that was tuning in on our YouTube channel, thank you as well. And if you'd like to support us and make sure that these Hangouts continue, you can go to our Patreon page at patreon.com/planets. And also, if you want to see the upcoming schedule of any future Hangouts, you can go to planets.life/events. So we will see you next week at 5 o'clock Hawaiian Standard Time, 11 o'clock Eastern Standard Time. And thank you. Thanks, guys. Thanks, Jeff. Thanks, Marcelo.
Good job.
Thank you very much.
Bye-bye.